You'll get an announcement. Okay, so you all should have heard that this meeting is being recorded. So we're going to go ahead and get started. There we go. So everyone, welcome to MapTime Davis. I'm really glad that you are here today. This has been one of the upshots of being work from home is that we get to have folks from a lot of different places joining us. So welcome to everybody. Again, I'm really glad that you're here. I think this is going to be fun. So my name is Michele Tobias. I am the Geospatial Data Specialist at UC Davis DataLab, and along with our Spatial Sciences Research and Learning Cluster within DataLab, we produce this workshop series. So a little intro for those of you who are new or haven't been to a map time before. So what is MapTime Davis? Literally, map time is time for maps. It's an international concept at this point. It happens in most major cities. And it is literally just making time for making maps because we get busy and we want to make maps as geographers and map makers, but sometimes we just don't have time. So Davis has its own special flavor of map time, which tends to be a little bit more on the academic side, but that's fine. Every map time is a little bit different. And ours this year, we're trying something a little different. We are alternating workshops like today's workshop with something we're calling studio. So next week, we'll have a studio discussion that is focused on this week's topic. So we're learning about machine learning today, and then next week at the same time on Tuesday at 10, we will have a discussion about machine learning, and you can bring questions, you can bring, follow up from today's workshop, you can bring tutorials you've found. It's going to be a nice discussion where we kind of follow up on today's learning. And again, today's MapTime Davis is always coordinated, at least this year, by UC Davis DataLab Spatial Science Research and Learning Cluster. It's being cranky about advancing my slides. There we go. Okay, so how can you get involved? So MapTime Davis actually, even though it's coordinated by a entity on campus, so it's coordinated by DataLab, we run on participation. So can't talk already. That's sad. It's only Tuesday. So MapTime Davis runs on participation. It requires people to give presentations. DataLab can't do everything, and I, as one staff member, I can't do everything myself. So we really want this to be a community. So you can, like you're doing today, you can come to workshops and to the studio discussions. You can help plan. We actually need helpers with planning and contacting folks and deciding what workshops would be helpful to have. So if you're interested in helping plan, I would be happy to have your help and the community that is already around MapTime Davis. We've got a few diehard regulars, and I think all of us would appreciate some more help on that front. You can also help at a workshop. Like today, I'm functioning as a helper for Alex and Lily. So you can do that as well. So you can also present a workshop, or you can help facilitate a studio discussion. So let me know. You can find my email on the UC Davis people search. Just search for Michele Tobias, you'll find me. Or if you're on the geospatial email list, you get emails from me way too much probably. So send me an email, let me know how you want to participate. And if you have ideas for workshops, I'm happy to hear them and help you either plan them or help find someone to give that particular topic. So MapTime Davis really is a community. It runs on you guys. Upcoming events we have for this quarter, we've got a few things left. So today we're learning about machine learning, and next week we'll be having a studio discussion about the same topic. The following week after that, we are having a joint mashup type workshop with the Davis R users group. So Ryan Peak is going to present about making maps with R. So if you attended 2 weeks ago, the figure discussion workshop with how to make journal figures, this will be a nice follow-up to that in terms of using R for making maps. And then the following week after that, on December 1st, again, we'll have the studio discussion about mapping in R, which hopefully will have a good crossover with the Davis R users group folks. So that's what we've got on tap, and that's it for my presentation. If you guys have any questions, feel free to put them in the chat about DataLab in general, or if you want to say, hey, I want to help with something, let me know. You can put it in the chat or you can send me an email. So that's our quick intro. Today we have Alex and Lily from Development Seed who are here to give today's workshop on machine learning. So I will let them take it away. I believe you both have screen sharing capabilities, so have at it.
Great, thanks. Hey everybody, good to see familiar faces and lots of new faces. I'm Alex. I work at Development Seed as a geospatial engineer. And we're a small geospatial and tech services company. So we help people build maps and do machine learning with satellite imagery. And Lily is a machine learning engineer with us. And most of this material is really cool stuff that she's developed and that she uses in her daily work. Right now, it's going to be an interactive tutorial. If you want to actually do the tutorials, you will need to have a Google account. UC Davis people, you can use your university account. In order for us to share data with you, please post your Gmail email address in the chat. And while Lily is presenting, I'm going to add you to a drive that has the satellite data already on it so that you don't have to spend hours downloading data. All right, so now for the fun part. Lily?
Cool. Thanks for the intro, Alex. I really appreciate it. I'm stoked to be here with you guys all. Let me get my screen share working. Okay, can you guys see my screen?
Yes.
Okay. Is it the presentation? Just want to make sure.
Yes.
Okay. Right on. Just one moment. Okay. Cool. Yeah, so today we're going to talk about crop type mapping with deep learning. So, essentially, like, I will talk about a few different, about machine learning in general and how it's used for many image-based problems. Crop type mapping with multispectral satellite imagery is just one of many. So for those who are less familiar, machine learning is a means of programmatically, for latency issues, I'm gonna stop my video just in case. Yeah, so what I was saying is for those who are less familiar, machine learning is a means of programmatically representing real-world problems such that they can be learned by computers. And there's a lot of machine learning algorithms, but a few classical ones include linear regression, decision tree, random forest, support vector machine, and naive Bayes. And then there's deep learning, which, as you'll see, is quite unique in the family of machine learning algorithms. So today we'll start with an explanation of deep learning. Then we'll discuss a few deep learning-based computer vision algorithms, followed by a deep dive into one of them called semantic segmentation. And then we'll go through a quick survey of some best practice notes and considerations to bear in mind when applying these concepts on your own. And then finally, we'll close with some specific notes on today's interactive tutorial. So yeah, deep learning algorithms are essentially designed to mimic the human brain's neural networks. They consist of layered architectures through which input data is passed, extracted for features, interpreted, and learned. And it's through this process that a neural network attempts to draw similar conclusions as humans would. At a high level, an artificial neural network, which from here on out we'll just refer to as a neural network, is marked by an input layer, which takes the raw input data, one or more hidden layers which apply feature extraction, and an output layer which predicts values from the learned features. A way you can think about a neural network is that it's a program that makes decisions by weighing the evidence. So by varying the types of parameters and their values, all of which we'll touch on soon, we can get different models of decision making. Deep learning algorithms can be supervised, in other words, with defined targets, or they can be unsupervised where the targets are unknown. But today we're just going to talk about a supervised example. One other important thing is that when it comes to computer vision in the context of deep learning, most neural networks are structured to support images with a depth of 3 channels. So the reason being for that is humans see in 3 channels, right? So the optical spectrum of red, green, and blue wavelengths. And circling back to the notion of these algorithms being designed to mimic human function, the nuances of vision follow in step with that. So that said, the thing is that the caveat is that said, like, you don't always have to use the red, green, and blue channels of, say, like a multispectral satellite image specifically. Sometimes it's going to be the other channels that will be more useful for your problem, such as like near infrared or shortwave infrared channels. You might even actually combine the spectral characteristics of more than 3 channels through the calculation and stacking of spectral indices. And a little hint, that's what we're going to be doing today. So yeah, here are some common deep learning based computer vision algorithms. Image classification is used to categorize entire images into 2 or more classes. An example might be satellite images with variable cloud coverage, and you want to know which contain clouds and which ones do not. So let's say you have a ton of these overhead images. This is a really great way to replace manual photo interpretation and sort the images into a binary set of images with clouds and images without clouds. Object detection is a step towards more refined inference. And with this type of algorithm, we can actually classify and detect the location of targets in an image, where there might be 1 or more target object classes. The product of this algorithm is 1 or more bounding box coordinate arrays with class labels for target objects inferred from the image. And we often use this type of algorithm to detect distinct features such as cars or planes from satellite imagery. And then moving further down the line of granularity, we come to segmentation. And this algorithm predicts the class of each pixel in an image, right? So pixels can have one of any number of I also can't speak today. Pixels can have one of any number of defined classes. It's oftentimes like one of the classes is background to contrast with the other foreground, otherwise known as like the target classes. In the field of remote sensing, it's common to use this type of network for problems such as land cover classification, or like today, crop type mapping, where you want to know what each pixel in a satellite image represents. And then lastly, I want to just briefly mention generative adversarial networks because of their interesting contributions to the space of deep learning-based computer vision. These networks are like, they're very new and they're very powerful, and they're often used for synthetic image generation and style transfer. And essentially what they do is they learn distributions from an input volume of images, and they learn the defining features and patterns that make real images look real. And then they take that learned knowledge to construct simulated representations that mimic the real images. So some common applications you might come across include image-to-image translation, 3D object generation, and super resolution, which is kind of like an alternative to pan sharpening. So semantic segmentation. Today, as previously mentioned, this is what we're going to be focusing our attention on. The name really does speak for itself, with semantics referring to the meaning, in our case, of an image, and segmentation referring to the division, in our case, semantics referring to the meaning, in our case, of a class, and then segmentation referring to the division, in our case, of an image, into separate parts. Semantic segmentation is often distilled into the combination of an encoder and a decoder. An encoder generates the logic or feedback from input data, and a decoder takes that feedback and translates it to output data in the same format as the input. The UNet model, which is, we're going to use a modified version of it today, is one of many deep learning segmentation architectures, and has a really great illustration of this encoder-decoder net structure. The left side of the model, the encoder, represents any feature extraction network trained for image classification. And the encoder learns the relationships between features in the input images with respect to their labels, and applies filters to the input data through a series of convolutional layers, where the output from each layer is a feature map, also known as an activation map. In the initial convolutional layers, the filters learn low-level features in an image, such as like lines or edges, and then progressively they learn more abstract features, such as combinations of lines and colors. The encoder downsamples as it moves from extracting low-level granular features to high-level abstract features. The decoder on the right side of the diagram filters for useful features at multiple scales and fuses the useful ones together. This is where a lot of the robust abstraction occurs. And it gradually upsamples as it filters at these different scales until finally it projects the learned discriminative features back onto pixel space. So there are other types of layers often floating between the convolutional layers, some of which induce non-linearity and randomness, so as to improve abstraction and generalization. And then following the decoder is the final classification layer, which computes the pixel-wise classification for each cell in the final feature map. And these models are often applied to computer vision problems where, of course, like regions of pixel space are representative of a unique class. And semantic segmentation enables us to directly localize and quantify these pixels of a predicted class. So now I want to briefly touch on a few components under the hood in deep learning. In a neural network, neurons in one layer are connected to neurons in the next layer. So when the inputs are transmitted between neurons, the weights are applied to the inputs along with the bias. The activation function decides whether or not the output from one neuron is useful or not based on a threshold value, and therefore whether it will be carried from one layer to the next. Weights control the signal, right? Or the strength of the connection between two neurons and two consecutive layers. In other words, like a weight decides how much influence the input of one neuron will have on the output, that being the next neuron. In a smaller way, it correlates with less influence from the input to the output. Biases are values which help determine whether or not the activation output from a neuron is going to be passed forward through the network. Each neuron has a bias, and it's the combination of the weighted sum from the input layer, where the weighted sum equals the weights times the input matrix, plus the bias that decides the activation of a neuron. In the absence of a bias value, the neuron may not be activated by considering only the weighted sum from the input layer. For example, like if the weighted sum from the input layer is negative and the activation function only fires when the weighted sum is greater than 0, the neuron's not going to fire. If the neuron doesn't fire or it's not activated, the information from this neuron is not going to be passed through the rest of the network. So adding a bias term of, let's say, like 1 to the weighted sum would make the output of a neuron positive, and doing so allowing the neuron to fire and creating more range with respect to weights, which will activate and hence be used throughout the network. So stated, like simply, bias increases the flexibility of the model by giving credence to a larger range of weights. And it's during training, the weights and the biases are learned and updated to fit the data and reduce error of prediction values relative to target values. So neural networks train in cycles where the input data passes through the network. A relationship between input data and target values is learned. A prediction is made. The prediction value is measured for error relative to its true value, and the errors are used to inform updates to parameters in the network, feeding into the next cycle of learning and prediction using the updated information. Bear in mind that unless your data set is like really, really small, it has to be fed to the model in smaller parts in order to avoid like memory overload or resource exhaustion. So here's some hyperparameters that are kind of like the most critical, and you'll see a lot in all of the various like network implementations or applications that you guys might come across if you haven't already. First is learning rate, which controls how much we want the model to change in response to the estimated error after each training cycle. And then there's the batch size, which determines the amount of data points that can be fed to the model during each cycle. So this kind of determines like, this is a very much so like a point of focus when you're looking at, your memory limits based off of like the hardware you're working with, or, it's also this is an important hyperparameter for considering the amount of time it's going to take to train your network. But stated otherwise, like batch size controls the number of training samples to work through before the model's internal parameters are updated. The number of epochs. So yeah, one epoch is defined as the point when all training samples, aka like the entire data set, has passed through the neural network once. The number of epochs controls how many times the entire data set is cycled through and analyzed by the neural network. We should expect to see the error progressively reduce throughout like the course of successive epochs. The optimization function is really important. It's what we use to change the attributes of your neural network, such as weights and biases, in order to reduce the losses. The loss function, which is also known as a cost function, measures how much the model needs to improve based on the prediction errors relative to the true values during training. And lastly is the accuracy metric, which is used to measure the performance of our model, right? So for example, a pixel to pixel comparison for agreement on class. Next, we have just some notes on for constructing, your training and testing data. There's some elements of good practice to bear in mind when you're doing this, when you're constructing your data for modeling. If you're working from one source data set, you need to split it into training, validation, and testing data. The latter two of which are not provided as learning material to the model during training. So like validation data is used to test the model or test the performance of the model at interim stages throughout the training life cycle, and testing data is used to measure the quality of the model after training is complete. A common ratio for splitting your data set into 3 component parts is 70% of the data points are used for training, 20% for validation, and 10% for testing. It's also really important to note that if you split your data randomly across data points, it's crucial to ensure that all the target values or classes are represented in all 3 component parts. Some application side notes. Generally speaking, after training the model is complete, we can use the same evaluation metrics for deep learning as we do for classical machine learning. So as an example, for like classification, confusion matrix, and F1 score is still applicable. But still there's like the really, looming question of when we should use deep learning instead of classical machine learning. One of the great strengths of deep learning is its built-in feature extraction, which can handle very complex or abstract data. And a good rule of thumb is like when the data is very complex and we don't want to do a lot of processing to define the features manually, deep learning is a great choice. Second to that, like deep learning is quite scalable and really does benefit from consumption of large volumes of data. In short, like when the data is pretty uniform and the feature space is not too noisy, or when the input data is not exceedingly vast, then classical machine learning is probably all that you need. But when those conditions are flipped, then I think it's worth considering deep learning. Another thing to factor in, though, is the cost of deep learning. Oftentimes, these algorithms require significant computational power to run, which amounts to expensive modeling. So the trade-off also hinges on a cost point of view. In fact, today we'll use a graphics processing unit, which is normally very cost prohibitive. But Google Colab is a very amazing thing that enables us to use GPUs for free. Typically, another thing is like typically when selecting a model architecture, you start with what you're trying to model, right? So is it to classify an image? Is it to detect an object? So on and so forth. And then within that associated family of algorithms, you check for the state-of-the-art model at the present time. So developers like all over the world are building and testing their models against these standard benchmark data sets so as to compare performances fairly. And you can reference the performance scores of the different architectures to decide which is best. But of course, you'll also want to keep in mind the notion of architecture complexity. Some might perform extremely well, but their architectures like under the hood are really enormous with a ton of parameters and computationally expensive to use. And a simple model architecture will comparatively cost less than a complex one, and may perform, if not slightly less accurately, but it's still going to do a really excellent job. So identifying the right balance of complexity and performance in relation to training time and executional cost is very important to factor in. Your choice of a loss function is a function really of the problem itself, right? If it's a binary classification problem, you might choose binary cross entropy. If it's a multi-class classification problem, you might choose categorical multi-class cross entropy. And both cross entropy entails compare the predicted class probabilities for, let's say, a given pixel and choosing the highest probability class. We'll actually use an adaptation of this loss function today for a class imbalance data set. It's called focal loss, and it uses class weighting based on frequency in the data set to tonify the losses associated with each class. And lastly, we can initialize the weights of the network to random values or all zeros and let the model learn the correct values, or which is a very popular way of doing things, we can adopt the trained weights from another model to expedite the learning process. So remember, in the initial convolutional layers, it's just simple features that are learned, like combinations of lines and colors. And since that is generally extensible to many image-related applications, we can adopt the weights trained by another model to learn those low-level features and start with that foundational knowledge. And this makes it such that the network only really needs to learn the high-level features you need unique to your training data. So this is actually something we'll also apply today in our tutorial. So stuff that's really specific to today's tutorial. Some of it was already mentioned in the intro, but we'll be implementing our segmentation model in Python using TensorFlow, which is an open source library created by Google for developing, training and deploying machine learning models. We'll also use the Keras API, which works as a wrapper for TensorFlow modules to make them concise and intuitive and kind of like human readable. Our code will be run on Google Colab, which is built on the precedent of Jupyter Notebooks, which are web-based interactive and executable code environments. And that enables like ease of sharing and inline instructions, and as I mentioned, free access to GPUs. The data we'll be working with is sourced from a past challenge hosted by Zindi, which is the first data science competition platform in Africa. The challenge is the 2019 Farm Pin Crop Detection Challenge, which encompasses Sentinel-2 multispectral satellite imagery across the growing season in South Africa, along with ground truth, crop type labels, and contextual information for the problem area. And then I mentioned the note about how a lot of these architectures are structured on or require input data, like, you know, in the context of computer vision with a depth of 3 channels. But today, instead of stacking the red, green, and blue channels of the Sentinel-2 image, we're actually going to make use of the multispectral resolution and calculate relevant spectral indices from the various wavelengths to stack as a 3-channel input image.
Hey, Lily, we've got a couple questions in the chat. I don't know if that, some of them I think might be good to talk about now before we dive too much into the tutorial.
Oh, okay. This was actually the last slide.
Okay.
And yeah. Okay, cool.
Whatever you think is best.
Okay, yeah, I'll just finish up on this, and then I think we'll do like a quick little question session and then jump into like the tutorial itself. But yeah, so essentially we chose 3 specific spectral indices for today's mapping application. The first is a normalized difference vegetation index, which measures healthy green vegetation. It's a classical spectral index that is it's really highly renowned and used in a lot of remote sensing plant phenology studies. The combination, it's essentially a combination of the normalized difference formulation and the use of highest absorption and reflectance regions of chlorophyll, which makes it robust over a wide range of conditions. However, it can saturate in dense vegetation conditions when the leaf area index becomes high. We also chose the soil adjusted vegetation index, which is similar to the normalized difference vegetation index, or NDVI, but it suppresses the effects of soil pixels. So it uses a canopy background adjustment factor, and that factor is essentially a function of vegetation density. And this index is best used in areas with relatively sparse vegetation where soil is visible through the canopy. And then the last one is the wide dynamic range vegetation index, which is similar to NDVI, but it uses a weighting coefficient to reduce the disparity between the conditions of the near-infrared and red signals to the NDVI. And NDVI tends to level off when vegetation fraction and leaf area index increase, whereas this spectral index, WDRVI, is more sensitive to a wide range of vegetation fractions and changes in leaf area index. Yeah, so with all this information, I think this is a good time for questions, and then after that we can move on to the actual hands-on tutorial.
Just as a reminder, everybody, if you want to post your questions in the chat, we'll ask Lily those questions verbally for you. So the first big one is, can you give an explanation of the difference between deep learning and classic machine learning?
Yes, I think really, so classical machine learning is not inherently designed to mimic the way that the human brain works, right? So these deep learning networks are kind of built off of the way that the brain's synapses and nodes are connected, and how they abstract. The thing about deep learning that's still quite interesting is that the way that the filters convolve around input data in these interim feature maps is it is essentially, if you boil it down, matrix multiplication, but it's still kind of a black box how these features are abstracted. So whereas like in a random forest, you can sort of like, if you will, like I'll use the word even like deconvolve, or you can map out how each feature contributed like explicitly to the final prediction. That's not necessarily something you can do with a neural network. So there's a lot of it's definitely a bit more of a abstracted type of machine learning, if you will. Like deep learning is a subset of machine learning, and so like it's definitely, I would say, a bit more of like the fringy version of it, or the fringy like type of machine learning, if you will. Because it, of course, like we still know very little about how the human brain operates, and so that factors into how much we can actually infer like what is going on in the internals of these neural networks.
You think you could elaborate a little more on how classic machine learning typically works?
Sure. So, well, it depends on the type. Like it depends on like the like what sort of like type of classical machine learning you're looking at, like whether or not it's like random forest or something like that. But essentially, you define, like one of the biggest differences is like oftentimes you're defining the features explicitly with classical machine learning algorithms. And you don't necessarily, like with classical machine learning approaches, you don't often train in these successive epochs. It's usually like one round of like learning, and the output of that learning round is essentially the final prediction. Whereas in deep learning, essentially the way that the networks are structured is there's forward propagation and back propagation, which I think are really useful to look at maybe outside of the context of this tutorial, because it's a pretty involved topic. But essentially, these neural networks have to train in cycles because they go through this weights update through the back propagation. So things are learned in the forward propagation, and then they're compared for accuracy relative to the ground truth at the end of that forward propagation, and the errors that are identified during that evaluation step are used to update the internal weights in back propagation. So that's not something that really happens in classical machine learning.
Great. So then we also had a little bit of a discussion going on about why can't you use the same data for validation and testing?
Yeah, that's a good question. It's not necessarily like prohibited, right? In fact, oftentimes like people do use data for the same data that they use for validation and testing, and that happens oftentimes because they're the data that they have access to is not a significant amount of data, so they don't want to be in a data in a like a data void scenario when they're trying to train their model. And I think the caveat is like essentially like using separate data for testing and validation shows that your model is able to generalize better, right? And essentially the validation data is also used to sort of inform like weights updates as well. So not necessarily like for the learning aspect, but it's definitely like kind of just factored into like how the model is like learning over time. But I think usually like it's best practice to separate the two to show that the model can generalize better. Also, I apologize for noise outside of me. I live in the heart of LA, so.
All right, so then we have a slight follow-up to that, which is what's the reasoning behind the typical 70-20-10 split?
Mm-hmm.
And is there a different ratio typical to classical machine learning?
Yeah, There's no very like scientific reason for why. We just want to reserve essentially as much data as possible for training, because that's literally learning material. And the more examples we have to learn from, the better, right? The more information we're going to have. The 20 and 10% split, I think usually it's better to have, I think like the most important thing that you have to account for is validation data. So testing data takes a bit of a backseat to that. You can, oftentimes in the absence of like splitting validation and testing data, it's going to be something more along the lines of 80-20, training to validation, where that validation serves also for testing. But there's no, I wouldn't say there's any immediate difference in how data is split for classical machine learning. It's probably the same.
Just trying to read through here to understand the questions, make sure I ask them accurately. There was a interesting question, which I think is a bit of a rabbit hole, which is, how do you know which is the best architecture for the neural network?
Yeah. So, right, this is an open research question. I'm pretty sure it always will be. So everyone's data is different, right? And different architectures are going to serve a different modeling purpose or a different modeling objective. And then, a different data set very differently, right? It's like you're kind of always going to be, unless you're working from a standardized benchmark data set, like I previously mentioned, you're always going to be comparing like apples to oranges. So this is a matter of experimentation, right? You're gonna first be thinking of the things that are important, right? Like, what am I trying to model? Am I trying to classify images like the toy examples, like images of cats and dogs, right? Am I trying to classify a set of images into dogs? Like, this is a dog represented in this image, vice versa, whatever. Or are you trying to detect the specific locations of things? Like, am I trying to find in an overhead image where let's say, just like I mentioned before, like cars and planes are located? Then you're going to use object detection. And within those families of algorithms, then there's like the complexities and the nuances of how many parameters are embedded in this model, how many parameters are needed to be learned. And of course, like the general rule of thumb is that the greater the number of parameters, the more amount of time it's going to take to train, because all of those parameters have to be learned. So usually that's the complexity of the architecture. The number of parameters is something really to bear in mind. Sometimes people usually will default to saying that a more complex architecture is going to produce more accurate results. And that may be the case most of the time, but sometimes that's really not necessary. Say your data is not extremely complex, like you're not probably going to need a very, very complex architecture to do that, or to achieve like a satisfactory result for your modeling objective. And so you might choose something that's a bit more lightweight, and you're going to take less time to train. It's going to be more cost effective, and probably a lot easier to, let's say, like package and share like via Docker or something like that. You're going to have a lot less code to have to sort through. I think there's one other thing I was going to say on this topic, but really, like, I think what you want to do is to take everything I just said, but also really take advantage of these, like, the performance scores that people publish about the different architectures on various forums, Top Coders, for example, and then like Papers with Code. Those are two really great resources to sort of like check on frequently to see and compare the performances of different architectures, because different architectures are emerging like every day, or spin-offs of architectures are emerging every day. And people capitalize, of course, upon each other's like various like implementations to make essentially like a novel implementation. So experiment, definitely don't try and reinvent the wheel. Use architectures that exist, and then I encourage you to like experiment with them and see like maybe if you tweak, maybe if you tweak like one layer or add in like a dropout layer to increase generalization or something like that, then you might find a really great implementation for your data set and for your modeling objective. There's no really like single answer to that question. It's really, there's a lot of different things, a lot of different variables that influence like the best network for your purpose.
All right, so one last question before we jump into the tutorial. Does deep learning perform better than classic machine learning when you have rare classes?
It's a super interesting question. Super rare or rare classes. Again, this is also an open research question. So the thing is like, okay, actually, this is a really great, today's data set is a great example of where that deep learning is not always like the best solution. So if you look, all this data was sourced from an actual like modeling competition, right? Like I said, it was the 2019 Farm Pin Crop Detection Challenge hosted by Zindi. And they published, this happened, of course, like last year, right? And they published the results and the top performers. And they published all of their code. And there was like, I think like some general reporting about like what they did in the various like GitHub branches. And I think it wasn't until the 8th or 9th placed participant that deep learning had even been used in any capacity. All of the like top 7 or 8 performers were using classical machine learning. They were using gradient boosting, a type of gradient boosting, and that's a really like interesting thing. Like this is a computer vision problem. We're doing a segmentation model, and essentially like so you can use classical machine learning for segmentation. I hope that's clear and that wasn't lost in the conversation here. But it's not like just because deep learning is robust and very new and very cool at the moment doesn't mean it's always going to be the best suited algorithm for your problem. So like if you have, like going back to the original question, if you have like really rare classes, it's worth, depending on like your resources and like how much time you have to work on the problem, like doing some level of like an ensemble approach, right, where you're comparing the performance of a deep learning algorithm versus like a classical machine learning algorithm is a useful study, right? It's going to be really useful to inform like what's actually best suited to your data set. And if that encompasses like really rare classes, then all the more reason to probably do a comparison of the two, because what you really want to avoid is getting pulled into the scenario where you're relying on deep learning and you're maybe using like you're spending money on graphics processing units and computing in the cloud and stuff like that, if you're not using Google Colab, of course. And then you don't actually need to use deep learning and all of the implications that it comes with. So I encourage you to study that as you go with the various data sets that you encounter and work with.
Thanks. That's, I think, an interesting place to stop with the theoretical questions. I would encourage everybody who has more questions or wants to discuss the ins and outs of machine learning to come to MapTime Studio next week and debate and discuss or ask each other all about the different options, because there are many and there is no one answer. If you're all looking for like, what is the one way to do it right, there isn't. And it's a really active field of research that's going on right now. So we're going to transition here and we're going to start showing you the platform and materials for today. I don't know if you want to stop screen sharing. I can pull up.
Yeah. Okay, should be good to go for you, Alex.
All right. Can everybody see my screen?
Yep, we can see it.
Great. So the material we're showing you guys today, it's material we developed in collaboration with NASA for the SEVERE program, which is partnerships, international partnerships to bring remote sensing training and build up remote sensing capacity around the world. And we're going to be, there's lots of lessons on here. We're going to be doing the one that's on crop type mapping with deep learning. And the way this is going to work is that I'll post the link in the chat in a second. In this page, there's an open in Colab link. So you could read through the entire Jupyter notebook we did. And you can see there's code samples and there's outputs. And so you could read through all of this. But if you want to really get into it and play with it and try it, you're going to click this open in Colab. And it's going to pop open this great Google tool, which is basically hosted Jupyter notebooks that Google lets you run on. There are limits on it, but you guys should all be able to use it well for today. There's a few tricks to this. One, when you first open it, the first thing you should do is do a file, save a copy in Drive. It will save a copy of this notebook in your Drive, and that allows you to edit. If you don't do that, then anything you change in the page will be lost. You can't save it. The other thing is that in this code, there'll be some steps to mount Google Drive. I actually haven't done it on this yet. It'll show up in this folder tab once you're connected to Google Drive. And that's where you're going to be able to pull data from and save results to. So you can just use data to and from your Google Drive, and you can check its status by looking at this folder icon here. And we'll show you that in the enabling GPU section, you'll be able to use the menus here to see what kind of runtime you're using. And you can see here that you're connected. And it says for me that I have a Python 3 compute engine with a GPU. When you're not using a lesson or a tutorial or working in Colab and you don't need a GPU, you want to make sure you actually turn off GPU use, because they deprioritize you if you use too much of it. So it's a free resource, but it has a few limits to it. Okay, so I'm going to go ahead and post the link to this material in the chat so everybody can pull it up if they want. And then we're going to work through interactively the first few parts of it so you guys can see how it works. And then we'll let you all run at your own pace through it. And we'll come back in a little bit later to answer some questions, which we'll always be doing in the chat, as well as make sure we talk about the sort of results section of this workflow so that you understand the whole thing.
Cool. So,
all right, so there's the link in the chat. So Lily, I don't know if you want to pull it back up and start running through some of it.
Yeah, 1 moment. Wait. Sure. Can you guys see my webpage?
Yep.
Right on. Cool, connecting, right on. This is just some, I will say that as you work through this, the markdown instruction should be pretty self-explanatory. So just make sure to read read all of those bits and pieces. It'll help you if you get lost or don't understand necessarily like a code block. Just, yeah, bear that in mind. You guys can check this out at your own time. It's a lot of stuff that I already said, so I don't want to recapitulate all of that. At the beginning in the setup notebook section, this is where we're installing the required Python libraries. One really cool thing that is specific to Google Colab is they have a lot of libraries like pre-installed. So anything that's like built by Google, like TensorFlow, for example, or Keras, like most of those core libraries are already installed in Google Notebooks. So you don't have to do that. So only the
Earth
yeah.
Engine is also pre-installed. Some of our other notebooks that are on the website use Earth Engine, and so you can see those.
Yeah, and when it gives you that little warning, just say run anyway, of course, because this is all just like essentially like a virtual. It's like this is like you're kind of creating like a virtual environment, right? When you're installing these libraries and working from this notebook. So nothing is really getting installed to your local machine or anything like that. Okay, so this might take just a second. And a lot of these guys right here, like the TensorFlow examples and TDFS nightly, these are kind of like just various like branches of TensorFlow code that provide specific functions that we'll use and that other people use. And then we'll import the focal loss. This is like a library that's used to just kind of like package up and use the focal loss function. So we'll use that today for the sake of simplicity. So this is all installed, it looks like. You can tell when that like progress thing stops spinning. That's when you know that your cell block is done. And if you guys want, like, see, there's so much like logged information from even just this cell right here. If you want to just like simplify like your landscape and not show all of that, it's not going to like remove like the execution of that cell if you just cancel out that logged information. So I'll do that just to keep things clean. This next cell block is you've installed some libraries and now you're just importing all of the libraries, including the ones already packaged into Google Colab. Right here, some of the important ones are Rust Stereo, which we're going to use for like image input output and like array operations. We're going to use that for working with imagery specifically, and also Python imaging library. Pandas for working with data frames. GeoPandas for working with geospatial data frames. TensorFlow, of course, for our machine learning components, as well as Keras. And Keras is, of course, like an extension of, it's kind of like integrated right now with TensorFlow. They've kind of collaborated, and so now you can import Keras as like as an API from TensorFlow. Pix2Pix, which is actually going to be providing our decoder layers, and essentially from TensorFlow datasets, we're just importing a function for showing the progress. And then focal loss, and then scikit-learn metrics. We're going to import modules that enable us to compute confusion matrix and F1 score, and that's what we'll use for evaluation. So that ran. Now we're going to mount our Google Drive.
So the word of warning on Google Drive mounting, there is a known bug that we've hit randomly with some people, and we are talking with Google about trying to find the solution, where the Google Drive will mount and as you continue to run code, it might disappear on you, which will affect your ability to run some blocks of code. If that happens to you, the first thing to try is you can restart your runtime. And if that really doesn't work, you might have to just read through the tutorial, and at a later time, you can go and grab the data from Zindi yourself, which is several gigs of data, and put it into your personal Google Drive where it's more likely to not break.
Yeah. And
yeah, hold on. There's a question about authorization code. So when you run that block there should give you a link, and you click on the link and it should open another tab and put the code in the other tab, and you copy and paste that back over.
Yeah.
It's a Google authentication thing.
Just make sure you will just press allow when you are sent to that link. And then after you press allow, you'll get that authentication code. Cool. So I would do that again to show you, but it's mounted. So next, we're going to just establish our root directory, which is where we're holding our shared data, right, in Google Drive. You don't have to change anything there. You also don't have to change anything for your personal drive, but if you want to write out data using this notebook for yourself, then this is going to be, as you can see, the path changes from shared drives to my drive. So this is for each of you guys that are working with this interactively. Of course, you're going to see these results mapped to your personal drive, to a folder within that called prop type. Set that, and then we're going to move now to our root directory where our data is. Next thing is where we're actually enabling the GPU. So we're searching for it, seeing what's available. And now we found one, and we're connected to GPU 0. The next section, we're going to get, not download from Zindi, but download the data that we've pulled from Zindi that's now on Google Drive. We have 4 different Sentinel-2 timestamps for training and within that validation, and we have 1 other timestamp that we'll use for testing. Cool. This is just essentially we're just establishing the variables for the timestamps, stuff we'll need to know later. The coordinate reference system that we're looking at, you map people are very familiar with what that means. Probably don't have to say it. Check out the classes. This is like a data frame that's just showing like this is the integer value, the class integer value associated with each class, and then these are the human readable actual categorical names, right, for each class. And we, as like a little thing to know later, we're going to add, you see 9 classes here, but we'll be modeling for 10 classes because we're going to be accounting for background, which is of a value 0. So these are all the, remember what I said, like background and foreground classes, these are all the foreground classes, the target classes. So now we're going to go through what it takes to process the Sentinel-2 imagery. In this first block, we're essentially just setting up a function to open the, as you guys, I hope that most people here are somewhat familiar with Sentinel-2. Essentially, like when you download Sentinel-2 image, if you will, or a Sentinel-2 timestamp, all of the different channels are separated. There's like a preview image that has like the optical, the RGB representation, but it's like a compressed version. So you really want to work from the raw JP2 images for each channel. So you get this like compressed folder that has all of these files, and then we open it and we essentially parse through to get the channels of relevance for what we're trying to do. And so we're being selective, right? We're just pulling the channels that we really need. Which are blue, green, red, and near infrared, right? And it's kind of counterintuitive the way that it's structured, because like normal like RGB representation would be like, you'd think like red, green, blue would be stacked in that order, but for Sentinel-2 it's actually like blue, green, red. So if you were to do like a concatenation of those channels, it would be 4, 3, 2, probably like. There's a little tangent note, but anyways, we're using RStereo to open the images and read the actual array and the array information. Opening them first enables us, of course, to do that, as well as like get the metadata associated with the images, like the spatial information, like the coordinate reference system, the transform, the data type, the image width and height and stuff like that, which you can also get from the URI. But anyways, that's what's happening there. The next one is we're actually providing the functions to calculate the spectral indices. So we have NDI calc. NDI, I'm just naming it here as NDI because this can be, the same function is so basic that it can actually be used for other spectral indices by just swapping the channels that are used. So just consider this NDI calc to be, for our purposes today, the NDVI calculation. The the wide range dynamic vegetation index calculation is here. Soil adjusted vegetation index is here. And then this is just a normalization function that we're actually not going to use this. We're going to normalize the tiles themselves once they've been, once those have been produced when we're constructing the batches. The reason we're transposing the images is because the way the rasterio reads images, I think it's like channels first and then width height. So we have to transpose that back to get like width height channels. And then in this section here, we're just essentially stacking, right? Each of these spectral indices produces, you know, in nature, what it manifests as a single channel image. So like an array of depth 1. So what we're doing is we're taking these 3 indices, we're stacking them together to create like a pseudo 3-channel image, where each of those channels is actually just a spectral index. Cool. Next function here is where we're actually applying labels. We're creating like a labels array now. What we're doing is we're reading the labels, that GeoJSON into, I think it's actually a shapefile, but it doesn't matter. We're reading that into a geodata frame. We're removing invalid geometries, and there's a lot of reasons I think like a geometry can be invalid, but this is something you really want to do whenever you're working on a geodata frame, because like if you have invalid geometries, like you can kind of like bang your head against a wall, like essentially it's going to, you know, yell at you and tell you that like your GeoJSON or your shapefile is like not useful. So anyways, this is a really important step to always do when you're working with geodata frames. We're going to make sure that the GeoJSON is mapped to the same reference system, coordinate reference system as the Sentinel-2 images. Then we're going to create an integer column for the crop like numerical crop ID class column. The way that the shapefile from Zindi is structured originally is that column is numbers, but I think it's of type strings. So we're essentially translating that to an integer, and so that's what this is. That's what's happening here. Next, we're creating essentially like not a dictionary, but like essentially we're pairing together the geometries for each polygon with the class value that's associated with it. And then in this line right here, we're taking the image metadata, including the coordinate reference system, the transform information, the image width and height, the image dimensions, the data type. We're getting a hold of that. We're grabbing that for just one of the channels of the Sentinel-2 image, because we just need to know essentially like what are the bare bones, like what's the skeleton of the image. And then, you know, once we have that like skeleton, we can essentially create an array of what's like just an empty array, and then take the labels information using the spatial metadata of the shapefile that's accounted for in the geodata frame, and essentially like burn those shapes into this empty array and use the spatial metadata from the single channel, one of the single channels of the Sentinel-2 image, to essentially like make that the same space and the same dimensions as the stocked index image above. So yeah, you're just creating a labels image in this function right here. It's kind of all you really need to know. And then what we're doing is we're also just checking to ensure that all of the classes from the labels exist in that labeled image, right? We want to make sure that all of the 9 classes, as well as of course the background 0, are burned into or rasterized into that labels image. So we'll print that out when this runs. Next thing is, this is just essentially where if you want, you can save the images to your local drive. We're doing this again with Rasterio. It's kind of just standard stuff right here where you're taking the raw arrays, you're providing the information, and like, for example, like we're not explicitly taking, when we write out the index stack, we're not taking all of the bits and pieces of that spatial metadata, or all of the bits and pieces of the original image metadata, because instead of a 1-channel image, it's a 3-channel image. So you can reassign specific components of the metadata when you're writing out images, and we're doing that here to change that to 3 channels, to support 3 channels. Same with the labels array, we're writing that out to file. You're not gonna have to do this today because we've already done that, and this block in particular takes a long time. So if you want to do that at your own free time, that's worth it, but not for today. The next thing is we're actually tiling the images, and this is important because, like, in machine learning, we work iterative. These models train iteratively, and we have to train in batches, and there's very specific dimensional requirements for these architectures, and you can't feed, like, an entire 10,000 by 10,000 pixel Sentinel-2 image to a neural network. It's going to choke on that, and it's like you're going to hit a segmentation fault, or I don't know, something potentially like gnarlier. But we work on tiles, so we break down larger images into smaller, like, windowed pieces, right? Common dimensions are like 256 by 256 or 224 by 224, 128 by 128. Really, like, that's kind of just depending on the network you're using. Today it's going to be 224 by 224. So we're setting up the tile images directory, and then we're using Rasterio to do a windowed read on the original images and slice the original image, the index stack and the label stack, into 224 by 224 tiles, and we're writing those out. We're making sure to save them in PNG format instead of JPEG, because PNG actually maintains that spatial metadata and it writes it out to an XML file. So you can use that XML information to reconstruct like a mosaic in the end. But that's what's happening here. We're processing over the index stack when that's set to true, and then the label stack when it's set to false. This is like a compilation of all of those above functions to do like the pre-processing workflow. And so right here, we're reading the Sentinel-2 image, we're calculating the indices and stacking the indices to get the 3-channel image. We're rasterizing the labels here. If you want to write about to file, you can do that in this section. Save the images, tile them, and then we have this like skip skip variable here where you can either write out, you just set that to true and you'll follow this component, or if not, if it's set to false, you're just going to use the data we've already processed for you that's in the sample share drive.
Maybe we'll take a quick pause here to just check in with everybody.
Oh yeah.
So yeah, a lot of the things in this notebook can take time, and it's always nice to make intermediate products when you're working along, because if you had to regenerate that every time you wanted to run these models, then you could be sitting for hours a day just waiting to rebuild your data.
Mm-hmm.
So hopefully this gives everybody a little bit of insight into how you might do this in the Python world, since I know a few of you at UC Davis are more in the R world. You can hopefully translate over and get a sense of how you would do it in the Python world. And this also highlights that it's important to just save data as you go along, because if you only have to go back one step, it's always better than having to go back and rerun all the steps.
Totally. That's such a good point. Saves you a lot of time and hiccups down the road, and allows you to troubleshoot.
Yeah. Okay. So we got a quick question. The index image.
Mm-hmm.
So the index image is a compilation of the different types of indexes that you calculated stacked together and then saved as a new image?
Yes.
Sorry, I was answering the question. Yeah. Hopefully that answers the question. So like normally you would get an image and you'd have bands. I forget what word you're using for bands here.
It's channels, yeah.
Channels, yes. Bands and channels, same thing. And so you would have like red, green, and blue in a photograph. You can store any values you want in those bands. And so we're calculating new values and we're storing each of those as a band, and then we're saving that as our index image.
Yep. Yeah, that was really well said.
Yeah, okay. The next question is about how do we visualize the inputs and the training data and the images we're making. And we're going to go further in the notebook now because we've got plenty of those.
Yeah, totally. You'll see that momentarily. Cool. Then I'm gonna, this stuff is, I think I'll move a little swifter from here on out so you guys can actually get to working with the code. That's just where you're pointing to where the data exists. This, I don't think I was running. Let's see, where did I leave off? This shouldn't take long. Cool, not ready to file, set that up. By the way, Google Colab kind of like sometimes is a little weird with reading data from Drive, and sometimes there's like strange latency errors. And so if this says like, if this is one in particular, like where if it says like it produces 0 for, this is essentially where we're checking the count of images in the image the training image directory and the test image directory. If it says 0 for either one of these, just go back up to this function, run it once more, and then this one, and then try this again, and it's going to produce the actual number that exists there. Sometimes for the first run, this has just been a weird thing that the first run, it sometimes says 0. So
the Google developers told me that the Drive connection in Colab specifically doesn't really like directories that have more than a few hundred files.
Yeah, so there's like 20,000 in the training image directory and like I think 5,000 in the test image directory. So definitely that could be, see, it's going to do it. So what I'll just do is like go up here. It's a little annoying.
So I'll point out that Google Drive isn't the only way to bring data into Colab notebooks. You can actually use Google Cloud Storage. We just didn't do that because that costs extra money to put stuff in cloud storage, on top of if you already have, you know, a corporate Google account or a university Google account and you have your storage paid for, Google Drive is going to save you some money, but it probably performs better.
Mm-hmm.
Do we talk about edge issues later on? I'm seeing a question about edge issues.
What do we mean by edge issue? Oh, see, okay, cool, we're good.
Oh, when you, the problem where you have an object that's on the edge of an image, and so you only get a partial.
Yeah. So that's so again, this is there's different ways of handling that issue. Sometimes it's not as important, right? Like if it's I wouldn't say it's as important with crop type mapping or lane cover classification. Usually it's really important for like features that are extremely dependent on their geometries. So a plane or a house or like a type of a building, like the geometry is like a hugely impactful feature. That's going to be a case where if that object is cut off at the edge of an image, of an edge of a tile or a frame, then it's going to complicate things and make it a lot more difficult to produce accurate representations and predictions of them. So one of the ways I've handled that in the past and that I continue to do very often is like when I'm creating the training data, instead of do like a windowed tiling of the original image, I actually will, if I have access to like the centroids of these objects, and usually you have that if you're creating training data because you have to have like labels. So if you can get the centroid of the object and buffer it into like a rectangular orthogonal buffer, then you can use that rectangular buffer to actually tile the images themselves instead of just doing like a generic windowed read. So therefore, like if you do that, then you actually have the object in the center of your tile. Like it's going to be there if the buffer is of a large enough size, and that's going to just take experimentation to identify the proper buffer size. Also bearing in mind like how much resizing you would have to do for each of those buffered clips to get it into the right dimensions, like 256 by 256 based off of your spatial resolution. But good thing to do is like I've always done just like buffer tile on the buffers, rectangular buffers, instead of doing like just a windowed tiling. I hope that makes sense.
Yeah, I think that's pretty cool. There is another method that some people use called super tiles, where they'll combine multiple tiles together in order to ensure that they have something that crosses. If they have something that crosses the border, that it's definitely the whole thing's in there. But I think it's a good point to highlight that in segmentation models, we're classifying pixels here, individual pixels. So there is really no edge. The sort of scenario that Lily was mentioning it is more of an object detection, where you're actually looking for a specific thing that has shape.
Yeah. Cool. So if that answers that question, we'll just keep going through. This is where we're getting all of the images associated with the training and testing lists. 10,000 images. The reason there's 20,000 files up there is because that includes the XML files as well. So there's 10,000 images, the actual PNGs for training, 2,500 for testing. In this section, so a peculiarity to this data set we're working with is that there's a lot of background representation. The amount of foreground pixels associated with the foreground classes is very, very minimal, which makes this a very complicated problem, a very complicated data set to model. Because ultimately, if you have too much background information, that's a form of class imbalance as well. That just means that the background class is overwhelming all of the others. So if we can model, if we don't attune to that imbalance, then we're gonna, essentially be in the process of updating weights. It's going to be we're going to be looking at the accuracy of detecting the background class, and that's going to look really, really amazing because everything is going to get predicted as 0. And then all of the other classes are going to be they're going to be kind of like left behind, and we're not going to learn those the way that we should. So we have to remove a lot of the background tiles. In fact, like 90% of them, because that's how much representation background has. So
to clarify real quick, background is pixels that don't belong to any of the classes we have training data for.
Yeah, exactly. Like it's like in this scenario, it's like all of the pixels that aren't a crop, right? Like an actual like type of crop. It's like the dirt or the soil or the buildings, the urban areas, or the river itself, like the water. Like that's all going to be considered background. So only the pixels that are crop types are actually going to be the foreground classes, and we really have to remove all of the extraneous background pixel space. So we're doing that here. The way that we do that is we essentially read the labeled image, and we check if the image maximum is 0. If the image maximum is 0, then we know for sure that it's a background tile. If it's anything greater than that, then we can be confident that it's a foreground class, because it includes 1 through a pixel of a value 1 through 9, which is a foreground class. So we do that little check here. This normally takes a really long time to do as well, because we're reading like individual images. So for the sake of time, we've just recorded the specific file names associated with background classes to a text file that's also on Google Drive, and we're just going to read those from file, and we're going to do the removal process by backing out 90% of those background tiles. This is where we actually do the background removal. You'll see that the number of training examples reduces significantly from 10,000 to 1,342. And then in this section, we're going to split the training data into training and validation. Since we're pulling the testing data from different timestamp, then we don't have to do that 70, 20, 10% split because it's coming from something else. But we're splitting the original like training data set into validation. And it's going to be, in this case, actually, we're going to do 90 and 10%. I guess that's what I chose to do this back when I originally created the code. So that's happening here. We're going to print out the number of training, validation, and test examples. This is where we actually visualize the data. So coming back to that question we had just a moment ago, what we're doing here is we're essentially we're only going to look at the foreground classes. We don't want to look at any of the background classes when we're visualizing the data. So we're doing that here. Again, we're doing that little check for the image maximum value. And we're just going to essentially like choose random, we're gonna like produce a random index, like number, right? To choose like of all of the training examples, like just pull random examples. We'll pull 3 of them, and we'll pull the original, like not the original image, but the index stack tile and its mask, its ground truth mask. We'll plot those. Takes a little bit of time to run this part right here. Any of the visualization parts, I sometimes take a bit of time to run. So, don't want to jump ahead, but
well, while we're waiting, there was a question about what kinds of methods can be applied to class imbalance and adjusting for class imbalance.
Yeah,
I know we have it somewhere further down in the code, but I don't know if you want to talk about like what kinds of methods.
Yeah, there are other methods, right? So like we're doing focal loss today. Another very like hands-on way of handling it is sometimes like, so we'll do a bit of augmentation in this tutorial, but like augmentation is essentially like a technique where you can multiply the number of examples that you're training, that you're working from for training, right? So you can take an original image, like an original tile, and you can flip it, right? You can flip it vertically, and it's essentially a new image. That's up for debate, but in the world of machine learning, like flipping an image vertically or horizontally is the production of a new image, right? Or you can apply like a Gaussian blur to it, or you can induce like random noise, or you can like do a crop where it's essentially like a zoomed in version of the original tile, or like you can do like a histogram like change where you're essentially like changing the color space. And so a bunch of different like things you can do to an input image to make it like a novel, like a new version of itself. And so in doing all these things, if you couple them together, you're essentially multiplying your data set. So they're coming back to like with the original question is like, if you have a class imbalance data set, instead of just relying on like a focal loss function or some variant on that, like you can actually just look at the tiles associated with the imbalanced classes or the lesser represented classes. You could just selectively apply augmentations to those. So you can only multiply or give greater representation to the classes that you know, in the original distribution are lesser represented. So if you have like a ton of like we could take all these foreground classes and apply a ton of different augmentations to them to get them to somewhat compare in number of examples to the amount of background tiles. So that's one option to do in conjunction with or in replacement of a focal loss function. Cool. We got a little plot of our training examples. These are just the discrete binary, like not binary, excuse me. These are discrete label images, and then this is the stacked index array. Yeah, that's what's happening here, and we'll use that same function to plot images as we go. But moving forward, This is where we're actually reading the tiles into tensors. So tensors are like the required input format and output format for use with TensorFlow. The image shape, we're defining it here just as this is a variable we need to refer back to time and time again. 224 for both width and height, and channels 3. Batch size, we're going to feed two, for example, like 2 of these guys are going to be what are included in one batch, one set of data that's fed to each iteration of the model during training. These are just a bunch of, what's following here are just a bunch of functions that are TensorFlow specific that essentially enable us to take those raw image arrays, read them into a TensorFlow style format, decode their image type, and then here are our augmentation functions. We're doing a random horizontal flip and a random vertical flip on the tiles. And so not all of them will be flipped horizontally, and not all of them will be flipped vertically. We're essentially choosing to do so randomly. We're doing a rescaling to make sure that the index images are of a type float. And type float is required for working with TensorFlow. So that's what's happening in this function in addition to applying those augmentations. And if your images were not already in the size of 224 by 224, that would happen here in this resize function. This is where we're essentially compiling all of those prior functions, those TensorFlow specific processing functions, and we're producing the data set, right? And we're shuffling the data set. That's another common thing to do in machine learning is prior to actual input to the model, you shuffle it just to make sure that there's as much like variability and capacity to generalize as possible. And then we reassign the data set to be just one of the batches. So this is the iterated element that gets passed through each iteration right here is the output of this function. Here's the specific configurations for training, validation, and testing. So for training, we're applying the horizontal and vertical flip. For validation, the only exception is that we're not applying those augmentations, and same for testing. Shoot, I forgot to do this part again. Running these as I go. I apologize. By the way, you guys can also work on this like as I'm working on it too. I don't want to hold you guys back from starting on the code.
One tip here is if you see a number next to a code block, it means you've run it. So that can help people in finding what you've run or haven't run yet.
Yeah, totally. Good point. Okay, cool. So now we're setting up some display code that we'll use as we train and test the model. Essentially, we're just producing like we're going to look at one of the sample images and one of the sample masks as a result of the processing from the configurations for training, testing, and validation. This is just a little display function that we're using to plot. Here we'll display one of the training images. Again, we're doing like a random choice type of thing where we're just randomly selecting one of the examples. So sometimes that might look like you're going to get something where there's like very little foreground, but there's still foreground. You can see that, but you might want to see something with more. So we'll do a different random choice. I'm going to get a different, again, still not too much, but yeah, you're going to get a different image because it's randomly selecting a different one. Do the same thing for validation. Make sure that our validation images look good. It's literally the same code, just swapping in the list of validation images instead of the training images. And changing swapping out like the processing configuration to the validation configuration instead of training. Cool, validation images look good. And then lastly, for testing images, we'll just check those really quick. You always want to do a check on your data to make sure that you've processed it correctly. Otherwise, you're going to run into some like black box issues where you don't know why things aren't going through, or like why you're everything is like printing out zeros because there's no learned weights or anything like that. So always make sure that your data is sound before you feed it into input for the model.
I would like emphasize that, because some of the later steps you get down to where you're actually running the deep learning could take hours or days. And you definitely don't want to feed bad data into something that takes, a day and then find out it was bad.
Yeah. So that's gonna be a waste of your time and just resources. And I think we've all been there. Almost done with this guy. It should take not too long. Cool. Well, that's running. Should just be a second, but essentially now we're going to get into structuring the model. We're going to take advantage of some prepackaged like layers that are already put forth through like one of a image classification architecture. We're going to use the layers associated with that for our encoder, and then we'll use images from the pix-to-pix code, which is another architecture for our downsampling or our decoder, or upsampling, which is our decoder. Sorry. Output channels is 10. Output channels is essentially like the output of our network is going to be the dimensions are going to be the image width and height, and then the depth is going to be 10, which is the number of classes, right? So it's 0 through 9. 0 background, 1 through 9 being the 9 foreground classes. So the base model is, like I just said, we're essentially taking a series of downsampling layers from MobileNet v2. That's an architecture. And these provide, like, these layers are essentially just a bunch of convolutional layers and max pooling layers. And the connections are like rectified linear units, or excuse me, the activations are rectified linear units. We're defining the input shape being 224 by 224 by 3, which is just our image, our tile dimensions. And when we say include top false, that means that we're not taking the final classification layer. Okay, that's still running, so we're not going to be able to run any of this until after that, but I'll just go through this. So this is essentially where these are the blocks. We're just providing the layer names for them, and we're compiling them together and creating the feature extraction model, which is these downsampling layers. And then down here, this is the decoder, or the upsampler, which is the other side of the unit architecture, where now we're taking the the convolved features from the downsampling layer, the encoder, and we're like we are essentially like downsampling them now, or excuse me, upsampling them back to pixel space. And we're fusing the important features together and creating more refined information from those learned like low-level, shallow, granular features learned in the encoder. So still printed out. Yeah, okay. This is where we compile the encoder and the decoder. So defining the input layer right here, we're defining the down stack. It's sometimes called like the skip layer. And then we're concatenating. We connect the encoder and the decoder through skip connections. And so we're doing that essentially like here. And then the last layer is essentially like the fully connected layer. And it's a conv2D transpose, which is just the inverse of a convolutional layer. And we are projecting essentially the last feature map into back to pixel space through an operation with a kernel, essentially a feature map with 10 channels, using a kernel size of 3 and a stride of 2. If you guys want to know what like kernel size and stride are, Also stuff that's probably like useful to look at outside of the context of this tutorial. These are kind of just like, standard elements that you look at when you're constructing a neural network, and you can vary these parameters. But that's that. And then padding is, I'll just briefly say the padding is important because like it almost is like falls in line with the idea of edge cases. Like essentially like the way that these matrix multiplications happen in a convolutional layer, like you have these kernels, which are the filters that are moving, like they're literally moving around the input volume, like the input matrix. And they're doing something where they're essentially multiplying weights with that input volume. And then they're calculating the sum of those weights. And then that produce like the next cell in the next, in the input that gets passed to the next convolutional layer, the next max, or the max pooling layer, the dropout layer. When you have these kernels that don't fit perfectly, like if they're say it's like an image that is like 28 by 28 or something like that, and you're like a kernel size of 3, and it's moving like at a stride of 2, so, or like a stride of 3, and it's going, 3 pixels, 3 pixels, 3 pixels, both in like the horizontal and vertical axes. Like it's going to get to the point where it like essentially it can essentially reach the point where like edge pixels are essentially like getting, like they're not being used because like the kernel stride or the kernel size and the stride don't allow for that. So what happens when there's an inconsistency between the image dimensions and your kernel specifics, like you can essentially do this padding equals same, where we're just buffering the input matrix to make it fit I would say the configuration of your kernel size and strides. Again, like just don't worry about that for now though. That's not finished. Okay. Sorry, I'm just trying to like go faster now because I know that we're running low on time. Yeah. And then this is, like I said, this is the last layer right here. And essentially that's what we're returning. So we're sending the inputs to inputs and the outputs to the product of that last layer. So in Keras API format, right, we're essentially now taking the input to that function, which is our compilation of the encoder and the decoder, is the only input like variable is the number of output channels. Just doing that here. This is our model now. This is our skeleton of a model. In this part, we're looking at, so in the Zindi data set, there's a CSV that shows all of the classes and the number of examples that are associated with each class. So you can actually look explicitly at about how many training examples correlate with each class. And that's, we're doing that here, and we're essentially just mapping the frequency of the class's representation in the data set. And then we're getting like an inverse distribution of like how much we would have to like bolster, or how much weight we would have to apply to each class to make it sort of like equalized, if you will. So in this dictionary right here, you're seeing like the higher values, that's an emphasis on that class because it has a lower representation. So like class 9, like we have to really like weight that class quite a bit because it has such little representation in the data set. And so the logic sort of like applies throughout all of these classes. And 0, the background class, we're not going to weight it at all because it's extremely represented. In fact, too much so. So we're not going to weight that. That's why that like 0 is 0. So that's simply what we're providing, like these class weights to the focal loss function. Or actually, like it's interesting that focal loss function is actually going to do that automatically. But the reason I included this code right here is to just give you a very like visual representation of that class imbalance. This is where you essentially are compiling now the model, the skeleton that we made. And so Keras like is very like cool in the sense that it has these like very these callable functions that work on the the model itself. So you're gonna have like model compile, model fit, model.predict. Here we're just taking that model and then we're choosing our optimizer. We're choosing Atom. That's kind of the most performant optimizer right now. Again, like this changes like over time based off of like development. But some other ones are like stochastic gradient descent or AdaGrad or AdaDelta or whatever. There's a lot of different optimizers, but Atom is kind of like the state of the art right now. And this is just the learning rate that works. But usually this ranges from anywhere from like 0 to 0.01 to like 0.0001 or something like that. But yeah, this is something that is worth experimenting with when you're training your own models. The loss, we're choosing the imported focal loss function. Gamma 2 is like this that factor essentially, like forget what it's called specifically, but it's used to kind of regulate the impact of like the weighting on the weight on the like the actual loss calculation. From logits, it's true. That means essentially we're looking at initially percentages or probabilities, and we have to convert that to like class values. So, or what it means is that we're looking at the raw probabilities and not the like the converted like integer classes. Choosing for metrics, we're just keeping it simple and looking at accuracy. These two bits right here, just essentially where now we're creating the mask. We're getting of the 10 output channels, we're choosing the one with the highest probability. So that's going to be the class that's predicted. And then we're plotting it here. So, and then right here, we're actually going to run a quick prediction with the raw encoder before anything has been learned. So remember, the encoder is the thing that's learning like the really low level or like shallow features like edges and stuff like that. And you can kind of see it looking at this input image and getting that. It's getting that information, but really nothing more refined than that. So it's kind of fun to look at a prediction with the encoder or with the untrained model before you've actually done anything. So that's what's happening here. Then we'll do some callback functions, which are essentially what we're doing. We're implementing these things to happen, like occur after each epoch. One of the things we'll do is we'll show a prediction on one of the test images after each epoch, as well as print out the ongoing accuracies for training and validation. We're going to do 100 epochs. Sounds like a lot, but it actually trains pretty quick because we're running on GPU. If you're running on CPU, it's going to take a longer time, but we have the advantage of the CPU here. So I won't continue trying to run things right now. You guys can do that. But essentially what's happening here is like now we're using that model.fit function. We're supplying the training data set. We're supplying the number of epochs, which is essentially the number of training samples divided by the number or like the batch size. So essentially we're like halving our training data set because the batch size is 2. So we'll have, I don't know how much that is, but essentially it's like training data set divided by 2 is the number of epochs we'll have. Validation, or excuse me, the number of steps per epoch. Yeah, so there's going to be each batch is the data that's run through one iteration, and so once we've run through each batch, that's one full epoch. The number of epochs is a hard-coded value here, 100. The callbacks, we're just defining that. It's what we're using to print the results after each epoch. So you'll get, after each epoch, you'll get the input image, its true mask, and the predicted mask. And then you also get the loss value, and you want the loss to be as close to 0 as possible. So hopefully during training, you're going to see that loss go down. It's going to start at a higher value and hopefully decrease closer to 0 over the course of training. That means your model's learning and improving. And then you'll get the accuracy of the training data, or on the training data, and then the accuracy on the loss for the validation data, and the accuracy for the validation data. And then we're gonna plot the progress of, or just the the training and validation loss over the course of the epochs, and kind of like interesting because the training loss sort of hovers a little bit. It starts to go down and then it sort of plateaus here while the that's the validation loss, I apologize, and while the training loss really goes down. But the model certainly learns, of course, as you're seeing here, like that image before training looked like this when it was run through prediction, and now it looks like this. So despite this graphical representation of the losses over time, like it's definitely learning. This section is where you're saving the model out. You can save it out to your personal drive. It's going to be a folder called model out, and then it's going to save out in like the TF saved model format. So it's going to have a .pb file. Forget what pb stands for. And then it's going to have a subfolder for variables, and the variables is going to hold like just kind of like different critical like binary files that taking all of those things into consideration creates like the information you need to load one of these trained models. You can load from a checkpoint, which is essentially like loading from one of those saved files, or you can just continue working from the model that's been trained in memory in this notebook. That's what we'll do. And then we're going to do the run predictions. Essentially, this is the same get predictions function with slight modifications that we use to print or to plot a prediction image after each epoch. This little function right here, or this like code block, is essentially where we're running prediction on one image. This is what we get from running it, one of the images, one of the test images, and then this code block is where we're running on all of our foreground test images. So just gonna print them all. I think we put a limit on how many. I think it's like 20 or something like that. Yeah, 20. We're gonna print 20 of them, or predict 20 of them and plot 20 of them. That's what's happening here. And then the last section here is where we're doing an evaluation. Essentially what we're taking is all of those, we're still working from like 20 examples, and we're essentially like creating like a flattened array of all of the predicted images and a flattened array of the associated ground truth masked images. So we have essentially what should be as close to like a mirror image of the predicted images and the ground truth images. We're gonna have a single array that's just like the predicted classes versus the ground truth classes, and spatially speaking, like those are the same. They should have the same index along those arrays. And then we're doing a confusion matrix operation. And confusion matrix is essentially like where we're comparing specifically like along these flattened arrays, like do these pixels agree, like do these cells of the array agree with each other, and so like do they have the same predicted class value. So that's what's happening when we're computing the confusion matrix, and we're also just checking really quick to make sure that in each of these arrays, the predicted array and the ground truth array, we have all of the classes represented. So good news is that in the predicted array, we're seeing that all of the classes were predicted. That's good. That means that our model learned all of the classes. Again, we're just going to check out the class names, and this is in literally sequential order to match up with 0 through 9, 0 being background, not listed here, but 1 through 9, that's matching up. That's what you can essentially account for in this categorical array right here. And now we're going to plot the confusion matrix, and we're doing percentages of agreement between each class. So the tree label is over here on the y-axis, 0 through 9, background through foreground classes. And then on the bottom, the x-axis, these are the predicted classes. So what you want to see, essentially each of these percentages right here is how often, you'd have like a pixel that was of value blah for the ground truth label, but predicted as something else or of the same thing in the predicted array, right? So any level of positive percentage here means that there was some level of overlap, some intersection of like one pixel was actually supposed to be one class was predicted as something else. Where you have that occur, where essentially like the predicted label and the true label are the same. So like 0, 0 or 5, 5, when you see that there's a high percentage of agreement in that area, that's good. That's what you want to see. In a confusion matrix, you really want to see this form of a diagonal line, because it means that the classes are agreeing with each other between ground truth and predicted. So this is good. It's not the best, right? There's still like obvious like examples of confusion where we're seeing high percentages where they shouldn't be, like this one right here. But generally speaking, this is the trend you want to see in a confusion matrix. This is used not only in semantic segmentation, but it's used in a lot of different like not even just deep learning, machine learning evaluations is a confusion matrix. And then from a confusion matrix, we can also check out like the F1 score, which is essentially the like median of, not the median, but essentially like the combination of the precision and recall. And so precision and recall are separately on their own, in their own right. They're also evaluation metrics, but they don't do a really great job at holistically representing the accuracy of your model, because they kind of like show very specific perspectives on something. But F1 score is like the marriage of the two and is a very common thing to use when evaluating your models. So that's what we're using here. And our resulting evaluation score from our F1 calculation is 75% accuracy. So again, like this varies depending on the complexity of your data and the quality of your model. This might go up or down, but this really is like all of this code here is going to be, it's just kind of like, you know, you can swap your own data and you can use all of the same like stuff that's listed here. It's kind of cool to see how this might change for you guys. And also I encourage you guys to try changing the learning rate, or try changing other stuff, if you will, change the spectral indices, maybe change the augmentation functions or add more augmentation functions in. There's a lot of different ways you can tweak this to do unique work with your data. I know that I just took the entire time going through this. I hope that it helps you as you try and do this on your own outside of this tutorial. And hopefully some of you guys got to work on this hands-on as I was going through it verbally. But since we've reached our time, I'll just like open it to any questions, like really quick questions, and then let you guys get on with your days and maybe try this out.
Thank you so much for this. This was really helpful. And I think for me, I personally am going to spend some time with the code and then also probably rewatch the video, which for those of you who are curious, we will be posting this video on the UC Davis DataLab YouTube channel, which is public. So you should have access. You can find that just with a quick Google search. So hopefully this will be up in the next couple days, definitely before next week. And we also, remember, we have the discussion next week on Tuesday from 10 to noon, same Zoom link to continue discussing machine learning. So, work on this and see if you have questions, and we can come back together next week and chat in a, less formal, more open discussion kind of situation.
Yeah, and also I am more than happy. In fact, I really hope that like any questions that stem from this, like you guys, please do reach out to Alex and myself. I really love like collaborating with people outside of Development Seed, or those who have joined within Development Seed. Like, bring your questions to me. I'm happy to answer anything that you encounter as you move through this or try it out on your own.
So I think we are just at time, and given that there is a lot going on today in the geospatial world on campus, I'm going to go ahead and say thank you. And I think we're going to end this here. But again, definitely reach out to Lily and Alex both if you have questions, and come to Maptime Davis Studio next week, and also post on the Geospatialist, you know, all the usual UC Davis channels. Or for those of you who aren't from UC Davis, you can find me on Twitter and things like that. So thank you, everyone. We're going to end this here and stop the recording. But I really appreciate seeing all of you here today, and especially big thanks to Lily and Alex for doing this.